Look.
3,
Here we go!
1.
Ooh. Come on. Yeah.
Let's go.
Yeah.
Do it.
What?
Yeah, heads up.
Hello, welcome back to Project Saros. I tried to fly my rocket CASCADE a few weeks ago to do another test of the 360 camera, but it never left the ground. It sat there on the pad and it burned through the whole motor, and eventually the motor case failed, the nozzle failed, and it burned through one side of my fin can, which is super bizarre. I've never seen anything like it.
Do you want to provide some thoughts here?
Well, we're definitely not doing 2 flights today.
So today, we're doing an anomaly investigation. In engineering, when something goes wrong, we do an anomaly investigation or a root cause analysis to figure out what went wrong. This is most useful when projects are really complicated, as often the failure modes are unexpected results of seemingly simple mistakes. And for really energetic things such as rockets, understanding how they go wrong keeps people safe. This is why when rockets fail, companies and governments use similar techniques to what I'll show you today to understand what went wrong before returning to flight. So the first step in an anomaly investigation is to collect your evidence. Sometimes for rockets, the physical evidence literally goes up in flames and you don't have any, but we're kind of lucky and we have a bunch of physical evidence to go through. And first up is the nozzle. When we found it, the nozzle was pretty clogged, but the centerpiece was intact.
Yeah,
You absolutely have a blocked nozzle at some point.
The nozzle piece is still intact here, but it is off-center a little bit. It looks like the nozzle carrier got kind of melty and it kind of shifted in its place. You can see a ring of molten metal on the outside. That is probably the motor case. The piece on the outside is actually the motor retention for the rocket. It's the aero pack. I probably can't unscrew it. I haven't tried that hard, but I probably won't. The bottom of the nozzle is also pretty gummed up, but the nozzle throat is still wide open now that that blockage from before got cleared. The next piece of physical evidence is the motor case, which got split in half.
Oh, what?
That's part of the case.
Yeah. It looks like it melted through. You can see pile-ups of what I'm guessing are motor mount tube and epoxy. You can like flake off some of it with your thumbnail, but this stuff is a lot stickier. So this is about where the forward centering ring was on the inside. All of this was sort of in this region of the rocket. Everything up here was fine. Like it looks like it got kind of warm and drippy up here too, but not nearly as bad as down here. So it was really contained to the bottom half of the rocket.
Looks fine.
The rest of the fin can is surprisingly okay, except for, of course, the side with its name on it, which is a bummer. I just painted it the day before flight, too. It's charged through on this side. It's a little unclear if that came from this failure of the motor case. The flames also wrapped all the way up here. The front half is still pretty okay. The aft centering ring is still mostly intact, even though it's very charred. You can see where the motor mount tube failed right at the aft centering ring and broke off for the nozzle piece. Motor mount tube still has like very thin layers in places all the way through. So that's the major physical evidence. In addition to this physical evidence, we also have footage, checklists, and checkout photos. And I'm so grateful for this documentation because, you know, when things go normally, it feels like it's slowing you down, but when things go wrong, it really, really helps.
At this point, I'm gonna go back and get as much footage as I have and try and assemble a timeline, because now I need to pack this up. I'm gonna get the SD cards I have now and get the rest of the footage later. Wish me luck.
Now that we got our timeline, it's time to identify the faults and the probable causes of those faults. Fault number 1, we didn't fly. There was not enough thrust generated from the rocket motor to overcome gravity and friction. Fault number 2, we had an excessively long burn. So we were expecting 4.5 seconds and we got about 2 minutes. The next failures are all the hardware failures. So motor case failure, number 3, nozzle failure, number 4, fin can failure, number 5. Everything forward of this forward centering ring, totally nominal. Flight computer's fine, onboard camera's fine, thank goodness.
Hey, so this next section of the video is just a tutorial on how solid rocket motors work, because the rest of the video is not going to make that much sense without it. So if you already know how solid rocket motors work, go ahead and skip to this timestamp. Otherwise, join me for the next section of the video.
This is a drawing of a typical CTI brand solid rocket motor. I've labeled some of the important parts that I'm going to talk about in the rest of the video. Most important is the rocket fuel, the propellant. This is front and center, and it's divided up into chunks called grains. I don't know why they're called grains. This is one of the great mysteries of rocketry to me. So if you happen to know why, please let me know in the comments. We burn this propellant to make hot, high-pressure gas in the middle of this rocket motor. That hot, high-pressure gas wants to go into the atmosphere. The atmosphere is much lower pressure, and so it goes out through the nozzle. The nozzle sits inside the aft closure. In this drawing and in my rocket motor from my flight attempt, the nozzle is a separate piece. The key feature of the nozzle is the nozzle throat. This is the thinnest part of the nozzle, and it restricts the hot gas from all immediately going out of the nozzle. And then this section of the nozzle expands it. And when it expands it, the gas goes extremely fast, which generates thrust. The aft closure does several things. It takes the thrust generated by the nozzle and puts it into the rocket using the thrust spring. Quite literally, the rocket sits against the thrust spring and then the motor pushes it. The aft closure also connects the nozzle to the motor case using this threaded section right here. The aft closure also seals the hot gas inside by using this O-ring. There's another O-ring on the forward closure that seals the hot gas going that way. So that brings us to the forward closure. The forward closure does the same thing as the aft and seals the hot gas inside. The forward closure also contains the smoke or delay grain. This grain generates a lot of smoke during flight, which is really helpful for tracking it. And it serves as a barrier between the main fuel and a black powder charge up here. That's usually used to deploy parachutes. So this will burn first, this will burn slowly, and then this will deploy parachutes. However, I wasn't deploying parachutes this way, so this part I emptied out the black powder. So that's why it says usually. The last piece on the inside is this green liner. The liner is very important because it protects the motor case from the hot, high-pressure gas inside. Without the liner, the motor case would melt. Last but not least is the motor case. The motor case keeps the high pressure from blowing apart the rest of the rocket. It's bent at the top to hold the forward closure in, and it's threaded at the bottom to hold the aft closure in. So I'm going to show you some parts. So this is a motor case. It's made of aluminum. You can see the bent part here, and you can see the threads here. Next up, we have an aft closure. This one is not the one I flew with, so the nozzle's a little bit of a different design, but you can see the O-ring, you can see the threaded section, and you can see the thrust spring. So this fits inside a liner. This is a used liner from the two-stage flight, actually. This fits inside here, if I'm careful, and this is the forward closure. I sort of misdrew where the O-ring was, but this side has the delay grain, this side is for the black powder, and it slides into the liner like so, if I'm careful. Ta-da. So now here's the liner. So the reason why it's pinched here is because these areas were exposed to hot gas the entire time. These areas were in between the grains. This tiny little gap exposes the liner to hot gas. There's sometimes this ignition grain, a solid piece of propellant right at the top that's designed to burn quickly. You put your igniter all the way up until it hits this, then this helps you light the rest of the propellant, generating that hot, high-pressure gas and getting out the nozzle.
See if you can name all the parts in this GIF of a solid rocket motor being assembled and fired.
let's talk about grain shapes. Propellant grains are hollow. Most of them have a cylindrical core in the middle. Some of them can have really funny shapes, like a cylinder but with fins. That's really funky, but we're gonna keep it. I kid you not, this is called a fin-o-cyl. Real creative. So the one that I flew has the cylindrical core off center, and it's called a moon burner. So the reason the grains have such different shapes is because they change the surface area on the inside. So when it burns, you can imagine it burns outward in all directions. So a cylinder gets a bit more and more area for an individual grain. And a fin-o-cyl gets this really funny shape, but this funny shape has a lot of surface area. So you're getting a lot of hot gas, a lot of mass flow, a lot of thrust from a fin-o-cyl. The moon burner burns out faster on one side than the other, so you get these moon shapes as the propellant continues to burn outward. So this actually affects my flight in a couple of pretty important ways. So the first way, remember how it burns out faster on one side than the other. That means that the liner is actually extra thick, just to help protect the motor case. The other way this affects my flight is because of the igniter. If the grain is offset from the middle, it's going to be closer to one side than the other. When I need to put an igniter into the ignition grain, the igniter has to go through the nozzle, but then it has to turn this corner to get all the way up to the top.
What is this? Green screen? A PowerPoint? Who am I? A professor? Now that we have a timeline and our solid rocket motor knowledge, it's time for a direct cause analysis. We're going to map our faults and then we're going to put our probable causes underneath them. The first two faults are connected because they're both a direct result of not having any pressure inside the solid rocket motor. Without pressure, we can't get the hot gas moving quickly, which doesn't generate thrust, and a higher pressure increases the burn rate. So without that high pressure, the burn time is much, much longer than expected. So the probable causes of not having enough pressure are as follows. We have our hardware failures. So we have motor case failure at ignition and nozzle failure at ignition. If either of these things failed, they could have not let the motor come up to pressure. Our third probable cause is an ignition failure. So if it didn't ignite properly, it didn't build up pressure, so on and so forth. Our last one for this is a propellant manufacturing error. So we had the wrong formula and the propellant wasn't burning right. I think this is pretty unlikely, but since we haven't disproven it yet, it is a probable cause. Next up, faults 3 and 4 are also connected because the nozzle screws into the motor case. Our probable causes for 3 and 4 together are first a fatigue failure. A fatigue failure is caused by repeated usage of a part. The thought here is my motor case is about 8 years old. I've flown it several times and it could have failed at the middle or it could have failed at the threads. The middle would result in the case failure and the threads would result in the nozzle failure. In addition, we could have had a shock from the igniter. Not an electric shock, but like a physical shock. So the physical shock of the igniter could have caused the nozzle to fracture off, or it could have caused a motor case failure. Last up for these is a liner burn through. The liners are only supposed to last a few seconds, so it makes sense that the liner would have eventually burned through after being exposed to hot gas for 2.5 minutes. Last is a fin can. And it is kind of least because it's pretty clearly a cascading effect from either the motor failure or the nozzle failure, or it could be due to radiative heating. We had the flame for a long time that could heat up the launch pad. Maybe the launch pad caught the fin can on fire. I think that's pretty unlikely, but I haven't disproven it yet. It's a probable cause. The purpose of this section is to collect as many probable causes as reasonable and then use the evidence to eliminate probable causes. Let's go back to faults 1 and 2. We can pretty quickly eliminate both of the first two probable causes because we have the video evidence. If the motor case failed at ignition, the fin can would have gone up in flames much, much sooner. I mean, it's made of cardboard, it's gonna burn. If the nozzle failed at ignition, we wouldn't have seen it fall out at T plus 3 minutes or so. So those two we can safely say are eliminated. That leaves igniter failure and a bunch of information I haven't told you yet. We were experimenting with custom igniters because on eclipse day, it's going to be really, really, really important for that igniter to go on the first try. And as many Rocketeers can attest, your igniters don't always work on the first try. So we decided to make some custom igniters, and I took one to the pad. The igniter had a lot of extra juice in it. It was much bigger than a normal igniter. This means we're up to ignition failure, and I'm gonna send it to whiteboard me because I did a little better job of explaining this in the garage.
So usually you put your igniter all the way up at the top next to this ignition grain. When you light the igniter, you start burning the propellant right next to it, generating hot gas. This hot gas starts moving down the motor to get through the nozzle. You start burning the rest of the propellant grains on all of the exposed edges. These edges, these edges, these edges, and they all start burning. And so you generate more and more hot gas. Now remember, the nozzle restricts the flow. So once you generate enough hot gas for atmospheric pressure, you cannot get enough hot gas out of the nozzle. This condition is called choked flow. So after the flow is choked, the pressure starts increasing. The gas can't escape, but you're burning the propellant. So since the gas can't escape, it has to raise the pressure. And when the pressure rises, you force a little bit more gas out of here, but not quite enough. Something else happens when the pressure goes up, and it's that the propellant burns faster. The pressure is going up and the temperature is going up in here, so the fuel is burning faster and faster. Now you're generating more hot gas, which is generating more pressure, and the nozzle is letting out a little bit more hot gas with more pressure. What keeps this thing from blowing up is two things. Number one is that eventually the burn rate of the propellant will stabilize with the mass flow out of the nozzle at a certain pressure. And the second thing is that even though the burn rate is getting higher with more pressure, the rate at which it's getting higher starts to slow down. For the more mathy among you, I'm going to do a quick graph of chamber pressure, PC, versus mass flow, M dot. M dot is how much gas, PC is how much pressure is inside the motor. For the nozzle, the mass flow increases linearly with chamber pressure. So I'm just going to do this dotted line. Pressure goes up, mass flow goes up, and it goes up directly proportional, so it's a straight line. For the rocket motor, it does something pretty weird. It goes up, but then it kind of curves over like this, and it keeps going up. This is the stabilization point when the nozzle eventually catches up with the burn rate of the motor. So they are at the same spot down here before the flow is choked, and then the motor burns more and more and more, and eventually the nozzle catches up. And this, I'm gonna call it operational point. You can call it your stable point, you can call it whatever, but this is where it stabilizes. The shape of this red curve can change with your propellant chemistry. However, this is generally how stable solid rocket propellants work. Even before it gets to this pressure, all of that hot gas gets forced through the nozzle and starts generating thrust. But once it gets to that pressure, it's generating its nominal amount of thrust. Once you have that amount of thrust, take off and you fly like normal. All of this relies on getting that choked flow condition right at the beginning. But Cascade never got there. Cascade never achieved choked flow. And I'm also over here saying that we have a really big igniter that may have broken the motor. So what happened? I hate to say it, but this is the embarrassing part of the video where I you know, just roll the clip.
So this is a moon burner.
Oh.
So it has to turn a corner, and it is not turning the corner. So I can see how well this igniter works at the bottom of the motor.
Send
or
it.
I could get a different igniter.
I think send it.
Yeah. Worst comes to worst, I come back this way, maybe faster. I mean, they're still at the pad. I want to see what this igniter can do. It's gonna burn.
So it's a partial moon burner. If it has to turn a corner.
It only has to turn a corner at the nozzle.
Can you just take the nozzle off? And then put the nozzle back on?
No, I mean, yeah, but I'd have to deintegrate. I'm not gonna deintegrate here.
Right.
Okay. Tape on this bench.
I mean, you have to light some of the propellant, and like it'll all eventually light.
Yeah, it might work. It's a lot of... That igniter is way more powerful than the igniter I otherwise put in it. God, my go fever is so strong. also reusing a motor cap.
So we know that the igniter has to turn a corner to get all the way up here. But what happened on my flight is I put it in here and I had this like big chunk. It couldn't turn the corner. It couldn't make it. And I thought, you know, it's probably gonna light enough propellant that it eventually chokes the flow, but that's not what happened at all. And it just burned from one end to the next, and maybe it burned a little bit in like this, but it was never enough to get that choke flow condition and generate pressure and generate thrust. So this explains faults number 1 and 2, the lack of thrust and the excessive burn rate. The hot gas never made it all the way up here until it had burned through all of this propellant. And it also kind of explains why we got different colored gas at the end. I'm willing to bet that this ignition grain made different color gas from the white flame of the propellant grains, and the smoke grain just makes a lot of smoke. That's sort of where I'm at here. This Moonburner motor also explains why it lasted so long. We had this double thick liner the whole time. So this probably saved the rest of my rocket. Without seeing the inside of the motor or without testing it again, I am not going to put proven, because I'm making a pretty bold assumption that the rocket motor end burnt the entire way. And I don't really know why the smoke changed the way it did. However, I am certain that if I moved the igniter to the top of the rocket motor, I would not have seen this failure mode. Unless the propellant formula was off. I trust the propellant manufacturers very much. I haven't had a motor like this fail before. The flame was the right color. It was an I-125 white long burning motor. I did check the mess reports, and there aren't any reports like this about the motor that I was using. As far as I could tell, it was correct. There's still a chance that it was still the wrong formula, but I don't really know how I would test it at this point. I think the igniter failure is a much bigger reason why this didn't work. First up for faults 3 and 4 is fatigue failure, and I'm going to go ahead and put this as unlikely. Because while I've had this motor case for 8 or 9 years, I've only flown it 6 or so times. I don't really have fatigue data on solid rocket motor cases. So, you guys, in the comments, if you have a solid rocket motor case that you have used a lot, tell me how many times you've used it and whether it broke. And if it did, how did it break? Let's get some data in the comments. Next up, igniter shock causing a fracture in either the motor case or the nozzle. We can also say eliminated by video evidence. Again, nozzle didn't fall out till 3 minutes in. This leaves liner burned through. And friends, this is another long one. So back to whiteboard me for a much longer explanation.
Say hi. Say hi. Yes. Say hi. Hello. Yes. Hello. Oh, Miss Carlton.
So now I'm going to talk about the motor case failure. So what I have here, this was the liner from earlier, this is the liner from the 2-stage flight. This is the exact same length as the motor that flew on this flight. And then I have one spacer because this case is a bit too long. And this motor also needed a spacer. It's actually, it's still in there. If I line these up, we see something pretty profound. And it's that there's a really big chunk missing in the middle. I'm pretty sure that this is missing from the middle, and it's not like this, and there's a big chunk missing here because of a couple of things. Number one, there is an O-ring in here. I don't know if you're able to see it in the GoPro. So if it burnt through this chunk, it would have burned through that O-ring too. So I think that these were together. Plus, there's something else really cool you can see. I'm doing this by hand, so I'm sorry if we're shaky. Not only is this chunk missing, but this is really rough. Like the surface finish is really bad here. And the bottom of this approximately lines up with one of the grain boundaries in the liner. And the front of this is also pretty close to a grain boundary. It's not exact, but it's close. This makes me think that this grain finished burning first, and it probably failed on the side that burned out first. This was all burnt, and about half of this may have been burnt, and then it worked through the liner on this side first and melted through the case here. So once this was breached, it eventually melted the rest of the way around. But like, I'm not 100% sure how it did that in such a perfect loop. I feel like it should be a hole on one side instead of like a pretty even hole on all sides. I'm a little mystified there, but I am pretty convinced that it was this grain, judging by how this pattern lines up with this grain. So now for the nozzle. The nozzle is really weirdly pushed over, and I'm not 100% sure why that happened. It looks like it happened pretty early because of how this buildup looks on the bottom. Like, it looks like it took a while for that to get there. So maybe there was some flow going around the outside. But also, the nozzle carrier material, this material that the nozzle sits in is kind of plasticky. I don't know what material it is, but I wouldn't be surprised if it melted through this, and when it was melting through this, it made it really weak, and then the nozzle kind of shifted during that portion, but it's really unclear to me when that happened. On the same vein, I think the nozzle failed here. So this nozzle's a little different, again, because this nozzle is a single piece, but I think that it worked through the nozzle carrier material and around the O-ring, and it failed right here at the beginning of the threads. I wonder if there are still threads under there. Let me find out if there are still threads under there. Okay, so I'm gonna try and figure out if there are still threads in there to see if I can get a better idea of why the nozzle failed. So I'm just gonna very carefully scrape. Oh, you hear that? Those are threads. This is amazing. Okay, so we know that it was the threads. The threads failed. Oh my gosh, this is so cool. So, okay, let me draw this out. So the hot gas worked its way through here and melted through the threads. And when it melted through the threads on both sides, this whole chunk fell out as one piece. Amazing. Content, baby. With all of this in mind, here is my best guess at the whole sequence of events. So number one, the igniter was placed in the wrong position, and when this lit, it started burning this way, but it did not choke the flow, and so we got lots of hot gas in here. So it burned through like this, approximately, which is part of why it took so long. One of the middle grains failed. I've drawn 3 here, but this is a 5-grain motor. This second grain finished burning. Oh, I totally misdrew this earlier. It failed at a grain boundary, and then it kept working its way up and around. It's melting the motor case. Now, at this point, this is all burned through. This is now mostly hollow. So now that we've burned through it, we're like maybe burning the smoke grain now. But what's really important is this is melting the motor case. Here's the crazy part. The motor case drips down into the nozzle, clogs it. When it clogs the nozzle, this forces what before was a hot gas flow into the sides here. It's already burning through this, like it's been burning through this slowly, but now that the hot gas is directed to the outside, it burns through this extra fast. So it finishes burning through the threads here after this is clogged, and then once it gets through, this whole chunk falls out. Which is nuts! Nuts, I tell you! Like, when does a motor case clog a nozzle and then the nozzle falls out? Ta-da! It was a bonus! So I'm actually gonna rearrange the chart a little bit because the nozzle failure was due to the aft closure burn through. And I am gonna put proof in this time because we saw the threads, we saw the O-ring inside the liner, and this also explains why the nozzle was shifting so much, because as the nozzle carrier was burning through slowly, the nozzle piece was shifting left and right. And then when it shifted to the right, a gap formed that allowed some of the sparks to go through. That's why towards the beginning of this video I said that the nozzle was super gummed up at the bottom. It was slag buildup from all the sparks that went through the gap, which is pretty dang interesting. So I'm also going to put liner burn through at the grain boundary as likely. I'm not going to put it as proven because I don't know where the grains are, and I don't know why the second grain up would fail before the end grain, which I think is pretty odd. However, I think it's pretty likely because it did sit there and burn forever. That leaves the fin can, and by the time the fin can burned through, there was just a lot of fire going around. The motor mount tube did have some thin layers still intact on the inside, but the motor case did fail right in the middle. So I'm gonna put motor case as likely here, and I'm also gonna put nozzle as likely because when the nozzle failed, there was an increase in the amount of flames, and then they like bent all the way up, because since the nozzle wasn't there, the gas coming out the bottom of the rocket was going much slower. And since it was going slower, it could wrap around. And for radiative heating, I'm going to put unlikely, because if that was true, we would have seen more flames on the back half of the rocket. But it was only one side, and that was the exposed side. Again, I'm not going to fully eliminate it because maybe it did contribute some heat, but I don't really have a way to know. I wasn't exactly pointing a thermal camera at this thing. Now we know the direct cause. We know exactly what shouldn't have happened and what caused the rest to happen. That was the igniter was in the wrong position. However, we still don't know the root cause leading to the igniter being in the wrong position. So I'm going to introduce our last tool, the Ishikawa diagram. It's also called a fishbone diagram because it looks like fishbones. Ishikawa does not mean fishbone. We've finally arrived! This is the skeleton of the fishbone diagram that we're going to be filling in the next few minutes. The fault or direct cause is at the head, and the bones coming off of the center are your categories. Sometimes these categories can be direct causes if you want to use this to do a direct cause analysis. I'm going to be using it for much more general categories, because I want to cast a very wide net to find our root causes. And yes, the pun is intended. The bones coming off of the categories are your primary causes, and each of these have contributing causes. Each branch from a primary cause to a contributing cause is when you ask yourself why a primary cause happened, and contributing cause is an answer. And sometimes your contributing causes have contributing causes of their own. But there's also an element of discretion here. You can keep asking yourself why into oblivion, and you can end up with nonsensical results or things that are just out of your control and aren't useful. So I've trimmed down the fishbone diagram quite a bit for brevity in this almost 40-minute video. For our purposes, the direct cause we're looking at is that the igniter was misplaced and we had an exceedingly long burn that led to hardware failures. And I'll reveal the categories as we go. The first category is people. That's mostly me. This is my project and I had some help, but it starts and ends with me. So what did I do to contribute to this fault? When I was at the pad, I had no idea this was possible. You bet your butt if this happens again, I'm not doing this again because I don't want to repeat this mistake. And I could say, why did I have this lack of knowledge? Oh, I didn't do enough reading. Again, this is discretion here. If I read all the time to figure out all of the things that could go wrong, I'd get nothing done. The big one here for me was that I was tired and stubborn at the launch pad. So why was I tired and stubborn at the launch pad? Because I didn't have enough sleep. Why didn't I get enough sleep? I didn't do what we like to call CRIMP. CRIMP stands for Complete Rocket Integration minus Pyrotechnics. We made it up on my college rocket team and it stuck for us. It's a really useful milestone where you put everything in the rocket together except your black powder charges and your motor. It's really good just to make sure everything fits together and you can assemble the rocket in a timely manner. And you may recall last time, there's a bajillion ways to try and manage time better, but my top choice for next time is just to integrate a few days before launch and then scrub if things aren't put together. I did do this some. I did integrate the flight computers before I left for LA, but I didn't finish the onboard cameras, and I spent a lot of time the day before on the onboard camera system. And I also hadn't painted the rocket yet, so that took a lot of time, and I could have slept. And I probably would have made more sound decisions had I slept. I wouldn't have had that great onboard video though, but was it worth it? No. So this is a classic example of scope creep. I wanted to add more stuff onto the rocket before the launch, and it just kept adding and adding and adding, and it got away from me. The next category is methods, and first we had to turn on the 360 camera early. The way I designed it, the 360 camera has to be turned on, wrapped up in Nomex, integrated into the rocket, and then taken to the pad. Unlike the flight computers and the other onboard cameras, which are turned on after the rocket is vertical. This meant that by the time I got to the pad, the 360 camera had been running for 25 minutes or so. That's part of why I didn't want to go back to the table and find a backup igniter. So why did I have to do that? It was a design constraint. And that's sort of where this one ends. The next problem with the methods was that there were checklist issues. Didn't leave myself enough time, nor did I dedicate a specific person to be my enforcer on the checklist. There were checks and balances in the checklist, like I needed to have a dedicated bag of pad stuff. And what was in the dedicated bag of pad stuff? A backup igniter. And part of the reason there wasn't a dedicated checklist person was because I wrote the checklist just for myself. I've been writing the checklist for me to read, which means it can get a lot shorter and more effective. However, in this case, I had run out of time, and I was skipping a lot of the checklist, unfortunately. So I felt like I couldn't give it to another person because I'd spend more time training them on how to use the checklist instead of getting the rocket on the pad. So this is a pretty easy fix. The third category is materials. One of the material issues was that I reused a nozzle cap. This is very similar to the backup igniter. I left the nozzle cap at the table. I didn't know where it was, and I found this nozzle cap that I thought would work, but it didn't actually fit that well. I had to tape it down with aluminum tape, and maybe if it had fit a little better, would have gotten some back pressure, burned more propellant. You get the idea. I've said this like 5 times. So why did I reuse the nozzle cap? You know what else is on that checklist in the pad bag? The nozzle cap. No time for checklist is our root cause here. Another material issue is the long burning motor, and you might be thinking, I planned to fly that long burning motor the whole time. I didn't. My motors came in late. Joe was nice enough to let me use one of the motors he has in exchange for one of the motors that I bought. I ordered my motors late because of our good friend scope creep. I wanted to optimize for 1 low flight and 1 high flight, so that way we could do the low flight first and fit 2 flights in a day. But
We're definitely not doing 2 flights today.
our last category is the environment. What were things that were around me that contributed to the fault? And really it was time pressure, because FAR is a popular launch site. Just not a dig at FAR. It's awesome to go out there and see all the people. But when I'm out there and the 360 cameras running, avionics are running, onboard cameras running, there are other people at the pads who are also waiting. That was part of that stack. It is a contributing cause to this fault. This is it. This is the full root cause analysis, and I'm going to highlight the recurring root causes of scope creep and no time for a checklist, because I think they capture what really happened here pretty well. I put the rocket together a few days before with the flight computers, and it was in a flyable state. I could have just flown that and foregone the onboard cameras, but it was Wednesday, and so I skipped my complete rocket integration step. I decided to spend more time on the onboard cameras. I decided to paint the rocket. We made custom igniters. All that was happening the night before launch. When that happened, I didn't have enough time to do my checklist thoroughly, and when I didn't do my checklist thoroughly, I started making mistakes. I made a real simple mistake thinking that our igniter was going to be good enough, and I got bit with the unintended consequences. I learned a ton from Cascade, parachutes, deployment, using a 360 camera and a rocket. I'm going to take that with me into the next vehicle, and I really have no choice but to start making the Eclipse rocket at this point. I know that I need to give myself enough time, and I'm running out. If you made it this far, thank you. I appreciate it. This is a really long video about me roasting myself for my simple mistakes. This video taught me a lot of important stuff, and the next ones will come out sooner and be more casual, because this took a lot of editing time. And if I'm being honest, I could have built another rocket in that time, and I have 7 months remaining. My name is Andrew Adams. This is Project Saros. Thank you for watching.
Hey, Andrew, when are we expecting main engine cut off?
But future you can do anything.
Future me is amazing. Remember that, future you. I'm giving you affirmation.